everyone. I am Dr. Hilmi and I'm going to continue with the course Numerical Methods MME6133 for Semester 1 2020-2021. So we are going to continue with our final chapter, chapter 6, or in our course would be the fourth course outcome, okay, where we have to design stable solution algorithm for partial differential equations related to mechanical engineering. So I'm going to give in this video it will be an introduction for this chapter where basically we are going to cover the topic of partial differential equation or PDE, and the assessment for this chapter will be test 2 that will cover 30% from your overall marks for this course. So let's start with the introduction of numerical methods. So in this chapter, we are going to cover two different kind of PDE, the elliptic equation and the parabolic equation. Okay, for introduction, we are going to know what is PDE and why we should learn PDE. Okay, we are going to see some application and we are going to understand types of PDE out there. So what is PDE? So PDE, or partial differential equations, is an equation that involves a function and or its partial derivative. So for example, we have df over dt is equal to d square f over dx square. So we have the function of f, okay, with derivative in the first order and second order. So why we should learn PDE? So basically PDE is being applied in many kind of field in the mechanical engineering or in engineering itself. So we can see or we can look into the application in heat conduction, fluid motion, Navier-Stokes, Schrodinger equation, and etc. So what types of PDE out there? So we can classify or we can differentiate PDE by 6 different types. From the first one, we can look from the order of the PDE. Order of the PDE is determined by the number of corresponding to the order of the highest partial derivative in the equation. So let's say we have an equation of d to f over dx square equal to df over dt. So the highest order for this PDE would be 2. Similarly, if we have another PDE D3F, so although we have different variables here, okay, we still can understand that the highest order for this PDE would be 3. The second type of PDE is the number of independent variables that is available in the PDE. The independent variables is the variables of the one that we can differentiate with respect to. So looking at the same equation that we have here, okay, we can say that in the first equation, okay, the number of independent variables would be 2, okay, where we have x and t. So we have 2 independent variable. For the second PDE, okay, the second equation that we have here, we have x, y, and t as the independent variables. So we can say that this PDE have 3 independent variable, which is x, y, and t. The third types of PDE is looking at the linearity of the PDE. So a linear PDE is one in which the dependent variable, the one that is being differentiated, in our case it is function f, appears only in a linear fashion. So let's say we have the same equation here in the first and second types. So we have d2f over dx square equal to df dt. So this is a linear PDE. So as we only have the dependent variable, which is f, appears only in a linear fashion. So both are linear. If we have d2f over dx square equal to df dt times tangent t, okay, so now we have in the independent variable is being multiplied with df dt, and therefore we can still say that this is still a linear. But if we have but multiply with f, so this PDE is already non-linear. as the dependent variables appears and multiplied with the derivative of the independent variables. Okay. The fourth type of PDE is looking at the homogeneity or homogeneous. So a homogeneous PDE is one in which every term only involves the dependent variable and or its derivative. So if we can choose the same example that we have, so d2f over dx square equal to df dt, and d3f over dx square times dy equal to df dt, both is homogeneous. Okay, but we have d2f over dx square equal to df dt plus square plus tangent t. So now we have two terms. Now we have two terms here that doesn't contain f, and therefore we can say that this PDE or equation is non-homogeneous. Okay, unlike the first one, all terms have the dependent variable f. Okay, but this one only have the two terms only have x and t without the dependent variables. So this is a non-homogeneous PDE. The fifth type is looking at the coefficient of the PDE. So the coefficient types can be either constant or variable. If you use the same example, so both equation here would be having a constant of 1. Okay, so we can say that this is a constant coefficient. However, if we have tangent x times d2f over dx square equal to df dt, so this is already a coefficient with a variable. So this is a variable as we have tangent x multiplied with the second derivative of fx. Sixth type of the PDE is shape of the PDE. Either it is parabolic, hyperbolic, or elliptic. So we are going to learn details on the parabolic and elliptic in the next chapter, in the next topic, in the next video. So we can explain the sixth type of the PDE by having a general equation. So let's say we have a general equation of. So this equation is a linear. And it is a second order of PDE. So we have, by using this general equation, okay, we can say that the PDE is parabolic when b square minus 4ac is equal to 0, where we use variable substitution to obtain x square plus y equal to 0, where this is going to be a parabolic shape of equation. Then the PDE is hyperbolic when b square minus 4ac is larger than 0, or using the variable substitution, we are going to obtain the x square plus y square equal to 1, which is the hyperbolic x square minus y square equal to 1, which is a hyperbolic equation. So, and the last one is when b square minus 4ac is less than 0, where we get x square plus y square equal to 1, and this is going to be an elliptic equation. So that's all for the introduction for today. We are going to continue with the next video on the PDEs and the elliptic and also the parabolic equation.